So, welcome once again to the second lecture of the day in signals and systems. Now, in the morning, we were looking at the idea of a dot product, right? And we saw that when you give a complex exponential to a linear shift invariant system with impulse response HT, what you get is the same complex exponential multiplied by a complex constant. So, it is a complex constant of the form h e raised to the power j omega, or rather h of j omega naught. It is a function of j omega naught, isn't it? So, this is a complex multiplier. This is a complex multiplier. And it depends on the frequency omega naught. Yeah, h j omega naught is in fact the dot product. It is like a dot product of impulse response with the rotating complex exponential, right. So, this relationship has a very simple and beautiful interpretation. It says that when you give a complex exponential to a linear shift invariant system, the complex exponential remains as is in form and comes out multiplied by a constant. That constant is really the projection or the component of the impulse response upon that complex exponential. So, it's a neat and beautiful interpretation. And in fact, now you can visualize the following. Suppose I can think of my input as a linear combination of several such complex exponentials. Then each of such complex exponentials will produce a complex exponential of the same angular frequency, but modified in this manner. And the system is linear. So, if I take a linear combination of many complex exponentials of different frequencies with appropriate amplitudes and phases, right, then I can get the output by finding out the output to each of these complex exponentials and then combining them in the same way. Yeah, you are saying, now take a minute to appreciate what I am saying. I know what happens to one complex exponential here. So, if I have an input which is a linear combination of many such complex exponentials, then I can find out the output by seeing what happens to each of these complex exponentials, which is what this tells us, right. Each complex exponential is simply multiplied by the component of the impulse response along that complex exponential. And you sum up all these complex exponentials at the output. Is that right? Let us now appreciate this a little further. Now, this is of course a dot product of the impulse response with a complex exponential of angular frequency omega naught. Is that right? This is, in fact, we will now give this a different name. We will call this the Fourier transform of the impulse response. What is the physical significance of the Fourier transform? It tells you the component of the impulse response along a complex exponential of that frequency. And in fact, now we can also conceive of how you can reconstruct Ht from its Fourier transform. In fact, now let us forget that Ht was an impulse response. Ht could be any function of time, and the only requirement is that this integral should converge. That integral may not always converge. Let us take some examples. Let us take the example of the RC circuit that we saw yesterday. Let us try to find out its impulse response. So, we must now be able to give a physical interpretation, isn't it? The impulse response. Let us find out its impulse response, and let us also find out the Fourier transform of the impulse response. And then we will also connect it to what we understood in circuit theory, right? We are all familiar with basic circuits. So, we can see how we can connect. So, we have to be able to see in signals and systems, we should be able to connect ideas that we are learning, the abstractions that we are learning should be connected to concrete examples of circuits, right. So, let us take the example of an RC circuit. Okay. We want to find out the impulse response of this. Now, you see, an impulse, a continuous impulse is actually not achievable, right. How do you get a continuous impulse? What is a continuous impulse? We need to take a minute to understand this. So, you see, we saw what a discrete impulse was. A discrete impulse is a sequence which is 1 at the point n equal to 0 and 0 everywhere else. This is very easy to visualize. There is nothing great, no rocket science about it. It is easy to understand. But a continuous impulse is a little more complicated. So, the situation is like this. How did we want to generate the continuous impulse? We said we have a continuous function of time, right? And we said we want to break this continuous function to very small little pulses, right? And we wanted to find out the effect of each, and you can, as if you make the pulses very small, then they are almost flat at the top, right? See what I am saying? If the pulses are very, very narrow, then if you are breaking this function down into very narrow segments like this from the time axis, it is almost flat if the function is continuous, right? And then you are thinking of very narrow pulses, right? But you want these pulses to stitch together into the function. So, ultimately you want the following situation. You want to start narrowing the pulse down and let the pulse have a height of, let us say, h naught and a width of w naught. Now, if you narrow the width down indefinitely, after some time the pulse will simply vanish, there is nothing in it. So, something in the pulse should remain even when the width narrows down indefinitely. And what we preserve there is the area under the pulse. So, now you have to visualize an object whose area remains and is held in spite of the width becoming 0. That is what an impulse in continuous time is. It maintains an area in infinitesimal width, which means that you can conceive of what it does under an integral sign, right. So, W0 tends to 0 and H0 tends to infinity, but H0 times W0 is maintained. So, this is an impulse. And if H0 W0 is equal to 1, then it becomes a unit impulse. Is that right? Now, the unit impulse is not a function. It is a generalized function. It is not a function because we cannot define its value at a point. That is not a correct way to describe that object at all. We should call it an object because it is not really a function. It is a generalized function. right? And the operation of the impulse is described under an integration sign. So, for example, if you have now, you see, we denote this when h0 w0 is equal to 1, we denote this as delta t, or unit impulse. And you have x of t, if you multiply xt by delta t minus lambda, so lambda is a fixed number, and integrate this with respect to lambda, with respect to t, I'm sorry. What are we doing? Let's envisage it. You have this function x of t, and you have delta t minus lambda. Lambda is here, and you have delta t minus lambda. Where this width starts tending to 0, right? The width starts tending to 0, but the area is maintained. Now, you can visualize what happens. When you multiply this white function by the yellow function and you integrate it, what does it do? It simply picks up the value of xt at the point lambda, because the area is 1. Unit area is multiplied by the value of the function at the point t equal to lambda, isn't it? Of course, for that, the function needs to be continuous at that point. Continuous at the point t equal to lambda. Alright. Now, this is the way to understand this is to think from a limiting point of view. First, think of a narrow pulse. A narrow pulse multiplying the function x and integrated will simply, the pulse, see, visualize a very narrow pulse here. What will happen to this very narrow pulse, which is yellow here? It will simply pick up the value of xt at t equal to lambda, and all the rest will be cancelled, right? And when you integrate it, it will simply give you the area under this yellow pulse. How much is that area? X lambda times 1. So, x lambda. So, that's what x lambda, that's how you get x lambda. Now, this is called the shifting property of the impulse. What is the meaning of shifting? Shifting means channa. That is the best way to explain Hindi. Shifting means channa. Essentially, shift means to separate out very fine grains or very fine, pollutants. Is that right? That's what shifting is called, isn't it? Now, here you must think of the impulse as shifting out one part of the function, capturing just one part of the function, capturing just one value in the function. Okay? And here now we can look at the property of the impulse, you see, and get a different interpretation for this. The impulse can equivalently be put symmetrically about 0. Nothing stops us from doing that. So, you see, when the impulse, you can put it, it doesn't matter how you place it around 0, because ultimately the impulse is going to contract to infinitesimal width, and therefore you could put symmetrically around 0, and delta t minus lambda is the same as delta lambda minus t. Okay, it doesn't matter. So, essentially the impulse, even if it is flipped around 0, it makes no difference. It's all just unit area captured into a point. So, it doesn't matter, flipping makes no difference. So, we can rewrite this expression as x lambda is equal to delta xt delta lambda minus t dt. Okay, x lambda is x t times delta lambda minus t dt. And now we have a different interpretation. You see, here you can now think of xt as a constant. And in fact, now we can, because of our way of thinking, we can also interchange the roles of t and lambda here. I mean, just for our way of thinking. We tend to think of t as the particular point in time, and lambda as a variable of integration. So, we can interchange the roles and we can say x of t is integral minus infinity to plus infinity x lambda delta t minus lambda d lambda. Right? Doesn't matter, it's just the name, it's just the name of the variables. Now, look at this expression and look at the expression that you had for discrete time. What was the expression you had for discrete time? You said x of n summation k going from minus to plus infinity xk delta n minus k. Is that right? Compare this and this. Do you see the similarity? Right? You see the similarity? The role of n is played by t here and the role of k is played by lambda there. Is that right? The similarity. So, what we were doing as summation in discrete time now becomes integration in continuous time. So, now you can see how you can prove the theorem of convolution in continuous time, right? Delta t produces ht. So, delta t minus lambda would produce ht minus lambda. And then, now this is by invoking shift invariance. Now, you invoke homogeneity. So, multiply delta t minus lambda by x of lambda, which is a constant, right? That would multiply ht minus lambda by x of lambda. So, let us go systematically. Delta t produces ht, the impulse response. Delta t minus lambda would produce h of t minus lambda. Okay, this is shift invariance. X lambda times delta t minus lambda produces x lambda into ht minus lambda. What are we invoking here? What are we invoking here? Homogeneity. And finally, xt, which is integral from here, x lambda delta t minus lambda d lambda, is going to produce yt, which is equal to integral minus to plus infinity x lambda h of t minus lambda d lambda. What are we invoking here? Additivity. We are invoking additivity. Is that right? So, the proof is very similar. Now, anyway, this was also meant to give you a full understanding of the impulse, unit impulse. But you see, now all this is an abstraction. So, here, we went from yesterday, we went from two concrete examples, the example of this RC circuit and the example of a mass in a frictional environment, right? We went to the abstraction of a first order differential equation. And we saw why we wanted to deal with abstractions, because abstractions help us conquer more than one situation at once. If you understand what happens at the abstract level, you understand what happens in all these situations. Is that right? Now, here we have continued to deal with abstraction. But once in a while, we should move from abstraction to concrete. Otherwise, we cannot appreciate what's happening. So, all this looks, very airy-fairy, so to speak, isn't it? What's going on here? So, we need to take an example. We need to go back to the example of the RC circuit. And we need to connect these ideas to the RC circuit. Is that right? Otherwise, we will not appreciate what exactly is happening. That means we need to demonstrate the impulse response of this RC circuit, and we need to show that you can indeed calculate the output of the RC circuit for a particular input, right, if you know the impulse response. So, let us do that. So, the first question is how will we find the impulse response? Now, can you find the impulse response by applying an impulse to the RC circuit? Well, can you apply an impulse in the first place? How will you get an impulse? Physically, what do you think an impulse is? What is? Yes? Lightning, yes, very good. Why don't you come and explain? That's very good, yes. Come and explain what you said. That's a very interesting example, yes.
So lightning is the example of impulse because it is there for very short duration and it is producing very large amount of power. So we can consider it as an impulse.
Very good. That's a very good point. Yes. So lightning is a very good example of an impulse. Lightning, can transfer huge amounts of energy in almost infinitesimal time, right? So it's a very beautiful example of an impulse in nature. But lightning is dangerous. No? Would you like to be struck by lightning? No, you take so much of trouble to avoid it. Would you like the circuit to be struck by an impulse? No, your lab will burn, isn't it? So we don't want to really apply an impulse and find the impulse response. So we have to have an indirect way of finding the impulse response. That means we should think of the impulse in terms of functions that we can apply to the circuit, right? Now let's look at the impulse in a slightly different light. Let's look at the impulse as a difference of two steps. The height h0 and the width w0. Now this can be seen as the difference of these two. So this minus this is the impulse. Can you see that? It's a pulse. First, let's start from a pulse. And then let's start making W0 tend to 0. Right? Now, in fact, without really losing any generality, we could put those at 0. So, we could say a unit step. Right? Yesterday, we explained the significance of a unit step. What is the significance of a unit step? It's like switching on. Right? To switch on is a unit step. So, the unit step is denoted by ut often. A unit step is 1 after t equal to 0 and 0 for t less than 0. What is the physical significance? It's like switching on a voltage to the circuit, right? Now, u of t minus w0 is this white minus yellow, right? Except that you need to multiply it by h, right? Now, if h0 times w0 is equal to 1, then of course you have h0 is 1 by w0. So you have, what is the unit impulse really? The unit impulse really is 1 by w0 u of t minus w0. And in fact, you are taking the limit of this as w0 tends to 0. Is that right? Now, is this a familiar thing that we do in calculus? Does this look familiar from calculus? What are we doing there? Does this expression look familiar from calculus? Yes? What? Yes. So what? Yes. So what are we doing to the function ut? differentiation. That's right. So, this is essentially the derivative. It's the derivative of the unit step. So, unit impulse is really the derivative of the unit step. Is it clear to everyone? This is an important step to be appreciated. The unit impulse is the derivative of the unit step. Is that right? Now, let us invoke linearity again, linearity and shift invariance. Suppose I knew the unit step response. I didn't know the unit impulse response, but I know the unit step response. So, you see, what I am saying is delta t is essentially limit as W0 tends to 0 of ut minus W0 divided by WC. And you see, if you know the response to a unit step, let's call it S of t. So you have a linear shift invariant system whose unit step response you are aware of. When you apply ut, you get S of t, right? Now for this circuit, do you know the unit step response? Of course you do. In fact, you can tell me, if I apply a unit step here, which means the capacitor is initially uncharged. If it's you're looking at the linear shift invariant system here, this capacitor is initially assumed to be uncharged, right? If I apply a unit step, what is going to happen to the capacitor? It's going to charge exponentially and then remain asymptotically at unit voltage. Is that right? So that's the unit step response. So the unit step response for this is very easy to calculate. But the unit impulse response is not easy, right? So let's see if I can get the unit impulse response from the unit step response. Is that right? So I have ut. Now ut of ut minus W0 results in, what would it result in? S of, yeah, shift. And what property are we invoking there? It's shift invariance. Yeah. Now ut minus W0 would result in St minus W0, and this essentially is invoking the property of additivity and homogeneity. In fact, I can multiply this by W0 and together use additivity and homogeneity. So I am saying the property of linearity. So because of linearity, and of course then I can take limits on both sides. That's right, I can take limits on both sides. So what is my conclusion? If I apply a unit impulse, I can get the unit impulse response by taking the derivative of the step response. So the unit impulse is the derivative of the unit step. Unit impulse response is also the derivative of the unit step response. Right? So let's write this conclusion. It's a very simple lemma. In fact, this lemma is very useful for obtaining the unit impulse response in many situations. So in some situations, you might be able to find the unit impulse response directly. There are many situations where this approach is more meaningful. You find the unit step response and thus the unit impulse response. So lemma Now remember that this conclusion has been drawn by invoking linearity and shift invariance. If linearity and shift invariance were not applicable, this lemma would not be correct, may not hold. Is that right? So now we have a tool. We know how to obtain the unit impulse response of this RC circuit. Let us do it. Let us do it. So let's find the unit step response first. We know the unit step. Actually, we know the unit step response of the RC circuit. See, it's very easy to write down. So the input is xt, that's the voltage input, and the voltage output across the capacitor is the voltage is essentially yt. So what is the unit step response of the RC circuit? It's, well, of course, it's 1 minus e raised to the power minus t by RC multiplied by ut, which means that now at t equal to 0, of course, is 0. As t tends to infinity, what happens? E raised to the power minus t by RC tends to 0, and therefore it tends to 1. And therefore, so in fact, you can sketch it. You can sketch the unit step response here for the RC circuit. It's going to rise exponentially, isn't it? And then go to the asymptotic value of 1. Is that right? Is this clear to everyone? Yeah? The unit step response is essentially an exponential which asymptotically approaches unit voltage. Now that you can see from the circuit consideration, isn't it? Now, have all of you understood this? This is very important, right? Let us now find the unit impulse response of the RC circuit. So, it should be possible to find it by taking the derivative of the unit step response. And we know how to calculate the derivative of a product. What will you do to calculate the derivative of product? You would use the product rule, isn't it? Take the derivative of the first and leave the second as it is, and then repeat it with the second. So, this would be derivative of the first. What is the derivative of the first? It's minus into minus 1 by RC, and keep the second as it is, okay, plus 1 minus e raised to the power minus t by RC. What is the derivative of ut? What is the derivative of ut? Delta t, that's right. Now, look at this. How much is this? Delta t multiplied by 1 minus e raised to the power minus t by RC. What does delta t do? Delta t shifts. So, it picks up the value of the rest of the function at t equal to 0. Is that right? How much is the value of this at t equal to 0? 0, is that right? So, therefore, this term is 0. Because delta t picks up the value of 1 minus e raised to the power minus t by RC at t equal to 0. Is that right? And therefore, this term drops out, and what remains is 1 by RC times e raised to the power minus t by RC ut. So, this is the unit impulse response. How does the unit impulse response look? Let us sketch it. It's essentially 1 by t by RC, 1 by RC, and an exponentially decaying function. So, the unit step response rises asymptotically to 1, and the unit impulse response begins at 1 by RC and drops exponentially towards 0. So, in fact, we can sketch it together. We have the input xt and the impulse response. Let us sketch it together. It's customary to denote the impulse like this. We often denote an impulse with an arrow, and the strength of the impulse is 1. So, we write strength is the area captured under the impulse. The strength of the impulse is the area captured under the impulse, right. So, the strength is 1 and it is located at t equal to 0, right. And what is the response? The response is the strength being 1 by RC, wherever we don't know what the values of RC are. It's 1 by RC and an exponentially decaying waveform. Beginning with t equal to 0. So, you see, what is the physical? You must also associate a physical meaning with this. You see, in the impulse, what does the impulse do? We are saying the impulse initially suddenly pumps some charge onto the capacitor, and therefore it suddenly, it brings the voltage on the capacitor. That means it suddenly pumps charge onto it, throws charge on the capacitor, and it raises the voltage suddenly. Now, this is again a little bit, I won't say contrary, but a little unusual in physics, because you're saying that, a unit, and what does an impulse do? It suddenly changes, it seems to change the voltage across the capacitor suddenly, isn't it? Which is, the capacitor does not permit a sudden change of voltage. So, how can a sudden change of voltage appear across a capacitor? Only when you suddenly deposit charge forcefully on a capacitor. So, what does an impulse do? It forcefully deposits charge upon the capacitor, right. That is the way one must look at it, right. Suddenly deposits charge, and as a consequence it raises the voltage suddenly to 1 by RC, and then the voltage begins to decay from there. Why does the voltage decay? Because the capacitor discharges it, because afterwards, after the initial spurt of charge, the circuit is unexcited. Therefore, the capacitor discharges across the resistor. How would the discharge take place? Of course, it would take place exponentially. It would exponentially decay. Is that right? That's how one must interpret this. Yeah. Now, you know the impulse response of the RC circuit. Now, you can go the other way. So, now you can ask, if I know the impulse response, can I find out the response to a step? How will I find out the response to a step? I must convolve the step, integrate. So, I must integrate, that's right, but how do I know I have to integrate? Suppose I didn't say step. In fact, let us take another, let's take a pulse. Let's take a pulse, a finite length pulse, and let's see what the response of this RC circuit is to a pulse. So, what is the physical significance of a pulse? The physical significance of a pulse is that you have kept the voltage on for some time and then you have switched the voltage off again. Right? Suppose you did that. Suppose you applied a long pulse starting from 0 and lasting until time t equal to 3 to the circuit. Now, I want to find out the output here. What should I do? I should use the principle of convolution, right? So, I can use the principle of convolution. Now, I have the choice. I can, convolution is commutative. So, I can either move this pulse across the impulse response or I can move the impulse response across the pulse. Both of them should give me the same answer. Is that right? Let us write down both of them. The output here, if this is xt is the input here, the output here, the voltage across the capacitor, would be either x lambda h t minus lambda d lambda or h lambda x t minus lambda d lambda. Now here I want to illustrate an idea. Both expressions are equally correct, but which might be easier to do here? This is also something that we have to impart when we teach students. The second one. Why the second one? The second one might be easier because it's easier to move a pulse across a fairly complicated waveform. It's more difficult to move a complicated waveform, isn't it? So when you have two waveforms, one of which is easy to move and the other one which is not so easy to move, it's better to move the one which is easy to move, obviously, right? So let us do that. Let's move the one which is easier to move. So let's fix the impulse response and move the pulse. So you have one h lambda is like this. And how does x of t minus lambda look? X of t minus lambda looks like this. I'm sorry, lambda equal to, it should be the other way around. See, for a fixed t as a function of lambda. Is that right? Is that correct? Yeah. See, x of t minus lambda, how do you get x of t minus lambda? You start from x of lambda. How does x of lambda look? X of lambda looks like this. And how would you get x of t minus lambda? You first take x of t plus lambda, which means you take x of lambda and shift it backwards by t. And then you reflect this about lambda equal to 0, which means that at lambda equal to t, you get what is at 0. And whatever is after 0 is put before lambda equal to t, right? So you get t to t minus 3. Is that right? Is that fine? Everybody understands this? So this is x of t minus lambda. And now this is multiplied by h of lambda and integrated with respect to lambda. What would the integral be for t less than 0? When t is less than 0, how much would the integral be? 0, because there's no overlap. There's no overlap of the pulse for t less than 0, right? So this quantity, so we'll prefer to do this, and this is equal to 0 for t less than 0. And for t greater than 0, how much is the integral? The integral is from t minus 3 to t 1 by RC e raised to the power minus lambda by RC d lambda, isn't it? Now please evaluate this. And then we'll see that we could have arrived at the same answer by a different route. Now please evaluate this. For t greater than equal to 0, or even greater than equal to 0 really, how much is this y of t, which is integral t minus 3 t e raised to the power minus lambda by RC d lambda times 1 by RC. How much is it? 110. Yeah. Let me do it for you. It's 1 by RC e raised to the power minus lambda by RC divided by 1 by minus 1 by RC, isn't it? And this from t minus 3 to t. Is that right? Is that right? Yeah. e raised to the power minus lambda by RC divided by minus 1 by RC, evaluated from t minus 3 to t. And of course, this 1 by RC and this, so this cancels and it leaves you with e raised to the power minus lambda by RC from t minus 3 to t. Now, yes, yeah. Now, anyway, can I see this as a difference of two steps? So, take this input xt. Can I see this as a difference of two steps? What are the two steps? If I take, which two steps am I subtracting to get this? Yes, so this is equal to ut minus 3, that's very correct. Now, can we invoke our property of linearity and shift invariance here to obtain this? If I know the step response, I can find out the response to u of t minus 3. How? By shifting. So, u of t minus 3 will give s of t minus 3. Then I can invoke the property of linearity, superposition, linearity, and this will give you s of t minus s of t minus 3. Is that right? So, now an exercise for all of you is verify that what you get there is the same as st minus s of t minus 3, and that is to be expected. The system is linear and shift invariant. So, no matter what route you take, you should come to the same. The circuit does not care what approach you use to find the output. The circuit's output is well defined, right? You can find the output either by using the unit step response, or you can find the output by using the impulse response, right? If you want, you can also find the same output by solving the differential equation. All of them should give you the same answer. Is that right? So, now this example illustrates several ideas. It illustrates several ideas about the unit impulse response, about the unit step response, the connection between the unit step response and unit impulse response, also about the calculation of the output given the unit impulse response. Now, we shall also connect it to the Fourier transform that we discussed. We also connect this to the Fourier transform that we discussed. You see, now let us evaluate that Fourier transform for this particular impulse response. The Fourier transform ht is equal to e raised to the power minus t by rc, 1 by rc ut, which is, tell me, it's integral 1 by rc e raised to the power minus t by rc e raised to the power minus j omega naught t dt. And of course, since there is a ut, you integrate only from 0 to infinity. It's very easy to evaluate. It's 1 by rc integral 0 to infinity e raised to the power minus t into 1 by rc plus j omega naught. Is that right? T dt. Well, t dt, that's right. So, how much is this? Integrated from 0 plus to infinity. Is that right? Is that right? Now, let us look at, again, let's look back at the RC circuit. So, you had this RC circuit here. What is the Fourier transform? The Fourier transform here is the ratio of the output phasor to the input phasor at frequency omega naught. Is that right? The Fourier transform, you see, it's the constant by which a phasor of frequency omega naught is multiplied when it moves from input to output. Can you obtain that ratio by some other means other than going on through all this impulse response and step response and all that? Can you do it by a simple circuit calculation? We've all studied phasors, no? So what are the impedances here? What are the impedances of this? What is the impedance of the capacitor? Yeah? So what would be the ratio of this voltage to this voltage? To this impedance divided by R plus this impedance. Now does this agree with this? Yeah? Yeah, I forgot the 1 by RC. You're right. There should be a 1 by RC factor. Is that right? Yes. Now it is the same. Yes. Is that right? 1 by RC. Is that right? Now do you see that the two match? Yeah. In fact, you can calculate this. So it's 1 divided by 1 plus j omega naught RC. And that's exactly what you get here as well. So now you see that the two different methods of calculation, whether you started with this impulse response and found out the response, to an exponent. So if you start with the impulse response and find the Fourier transform of the impulse response, or you did a direct circuit calculation, it all gives you the same answer. Is that right? So this is by voltage divider. Essentially, it's a voltage divider principle applied to the impedances. I think all of you are quite familiar with this. Is that right? All of you are quite familiar with phasor analysis. So phasor analysis gives you the same answer as you get from system theoretic calculations. Is that right? So this tells us how all these ideas can be interconnected and how you could explain these concepts of impulse response, Fourier transform, right, by using the simple example of an RC circuit. Is that right? Very good. So we'll conclude this lecture here, and now the next instructor will take your session, right? And then you will take your lunch, and I'll meet you again at around 2:15. Yes, the question. Yeah. Yeah, so you will have tutorial sessions, right? So you'll be, in fact, now I have given you one example with an RC circuit, right? I would recommend that you can, with the teaching associates, you can work out a few more tutorial examples. Teaching associates will work out a few more tutorial examples. And perhaps you can also go to the lab and set up a circuit. But I don't know, so many people going to the lab, they can figure out if they want to go. But you can work out tutorial examples. You can work out tutorial examples for more complicated circuits. Right? In fact, you should design such problems yourself also and discuss them in your tutorial sessions, which you are going to conduct yourselves, right, with the help of my TAs. That's right. But has this been appreciated fully, this example of the RC circuit? All right. So we'll meet again at 2:15. And now you have the next instructor coming in.